Hey everyone, welcome back to our Lunch and Learn series with Scott and Mike covering the technical monographs that were produced through the working groups in the SCTE. Today, we're actually going to approach the first of the technical monographs, which is, what is the decibel? So Scott, why don't you remind us who you are, and then we'll jump into the content.
Well, I'm your friend who's known you for probably 10 or 15 years now, probably 15. And we like to nerd out on cable. We used to work together, and now we're kind of working together again with these monographs.
That's right. So we've been friends for a very long time. My brother from another mother in another place. And so we're Scott and Mike, and we are talking about standards, but specifically the technical monographs that have been produced and are available for download at SCTE.org. So on the screen, I'm going to see if I can get this little highlighter thing working. Ooh, laser pointer, yes. So if you go to SCTE.org, on the header bar, you can get to standards. And then inside of the standards page, you can click on the download approved standards page. And that will bring you to this table. And from here, then you can actually type into that search bar the number 293, and that will take you to these technical monographs. And this, the first of which is called, What is the Decibel? Okay, so what is the decibel? So why does this thing matter, Scott? And how is it not confusing?
Well, it is slightly confusing for people who are new to the topic, but I'll tell you one of the reasons I think it matters. Um, if you and I are working together and we are trying to share signal levels at different locations so that we can think about it mentally and troubleshoot and oh, I was at the amp and I had this value and you'd had that value. Would you rather I tell you that I had 23 dBmV, or would you rather I tell you that I had 42.381 microvolts? Like, what would be easier for you to remember, right? And what would have more meaning? So that's one of the reasons I think that we use the decibel. Another reason, and I know you're going to get into it, is there's two different uses for it, and one has to do with gain, and the other has to do with an absolute value.
Yeah. Yeah, so this is logarithmic math, and it can be a little bit confusing. And I remember the first time that I was trying to understand this, it was very confusing. But it uses logarithmic, specifically base 10 logarithms, to take really big numbers or strings of numbers, whether they're positive or decimals, and quantifies them in ways that are easy to understand and express. But what is really also important is the decibel itself without a suffix. And we talk about suffixes. I have the example dBmV is the suffix, are not to be used to express absolute values. And for those of you that know Ron Rannick, he's very, very specific about this. If you try to communicate an absolute measurement, say the amplifier was putting out 43 dB on channel EIA 116, he'll say, no, it's 43 dBmV, right? So the important thing to remember is that dB within the same category can be used to easily communicate change or ratios, relationships between two like things, like gain, return loss, isolation, etc. However, it cannot be used to express an absolute value, like at the tap, I had 10 dB of signal coming out of the port, right? We
Yeah,
use it a lot.
we say it that way, but your description of that is absolutely correct.
Yeah, and I believe it's accurate. We can still continue to communicate in the cable vernacular because there's a whole bunch of that, right? And I don't want to be nitpicky about it, but if we're gonna, talk about the academic definition of what a decibel is, then it is important to say that it is expressive of a ratio or relationship between two like values, not a singular absolute value. But it is very important. Okay, so moving on. Why does it matter? this is one of those ones that really kind of blew my mind, right? And we talked about it's all about the ratios. And the first time I heard this, not to get too nerdy, but we were actually combining two power values. So let's imagine that we were in the head end and I had a channel 3 modulator that was outputting 60 dBmV of level on channel 3. And then I took another modulator, also on channel 3, 61.25 megahertz analog, that was also outputting 60 dBmV of amplitude, and I combined them together using a combiner. In my head, simple math dictates that I would have 60 plus 60 minus the loss of the insertion, right? So I would have somewhere in the neighborhood of 117 dBmV of combined power when I combine these two things together. What do you think happened?
So what you're saying is that you have 120 minus the loss.
Yeah.
And were you, just remind me again, they weren't the same frequencies, were they?
They were. Yeah, I was trying to combine them together to see if I could get them to sum and equal 120 plus or minus.
They'll sum, but they won't no, because there's a logarithmic function here. You're attempting to trick me and the rest of the listeners, and it almost worked. Good job. No, in fact, ooh, I know the answer.
Yeah,
It's 60 dB.
that's right.
Because you are going to create a doubling in power, and in accordance with your chart, we're going to add 3 dB. And then we're going to run it through a two-way split backwards as a combiner, and we're going to lose 3-ish dB. We got these people that are going to argue it's 4 or 3.5 or whatever. We don't have to go into that, but in the all actuality, you're going to end up with the exact same amount of signal on the output side of the combiner.
That's right. And that's what blew my mind, right? Because in simple math terms, like, and we're all used to simple math. You take 60 and you add it to 60, you get 120. But in this case, when we're talking about logarithmic math, when you add 60 plus 60, you get 63. And that's where my head exploded. And I had to kind of go down this road to understand logarithmic math. And there's an example in here where we talk about stereos. And let's say, we're comparing stereo systems. And I say, oh, hey, I have a 100-watt stereo system at my house. And you went, hey, I have a 200-watt stereo at your house. Mine is twice as powerful as yours. Well, in principle, in general math terms, you would think that that's right? 100 is half of 200, or 200 is twice as much as 100. But when you're talking about the actual power levels in logarithmic terms, you would look at the ratio between the two, power 1 and power 2, with 200 over 100, and you get this, 10 log 2, and it comes out to 3. Again, math is funny. So if you increase your power or double your power, the amount of increase in dB or decibels is 3. And inversely, if you decrease the power by half, your decrease in decibels is also 3. So go back to my 60 plus 60 equals 60. That's exactly what happened, right? You took two like powers, you combined them together, and then you ran them through a combiner that has loss of approximately 3 dB, and you end up with right back where you started from.
I just kind of thought about something interesting as I'm looking at the charts here. Typical amplifier gain, 30 dB, that's not unheard of, meaning that's a somewhat normal gain figure, although they're getting hotter and hotter, we're getting more gain.
Yeah.
But I've never stopped to think that an old school 750 Moto Bridger with a 30 dB gain in it has 1,000 times the power from the input to the output, and they do that with only 3 amp chips in the stages, and they do it with a noise figure that's really totally acceptable, if not outstanding, right?
Yeah.
It's pretty
Yeah.
interesting to think about.
So that's what's cool about the DB, right? Is when you think about it in terms of that, you end up with these really big numbers, like a million, right? A million times change in power is actually 60 dB. It's much easier to communicate 60 dB of change in power than it is to say a million or a millionth in, the inverse direction. So you can say, well, my power decreased by 1/10,000,000th of a, a change in power, or you can just say, well, it's 30 dB lower. So I
Well,
think that's the real power.
Yeah, that and it's so much easier. I mean, maybe it's because it's inherent and it's built into the business and we've been doing it forever. But could you imagine, hey, how much did you lose on that piece of 750 cable going from the node over to the launch amp? Oh, I lost 890,000 times the power. Like, what is that? I don't know what that means.
What
Uh,
does that
and
even
and
mean?
and maybe if we started it out that way in the 60s when cable began, we'd know what that means. But somehow I think this is the right settling point in terms of how to present this, calculate it, and then communicate it to others.
Yeah. So how much loss was in that section of trunk? Oh, 1/10,000th of a millivolt. Or, yeah, exactly. So dBs are extremely useful, right? Okay. Now, in order to put it to work, and we started off by discussing the relativity of the relationship between two like values. Now, in order for it to make it mean anything absolute, we have to add the suffix. So we talked about the amplifier gain example. For instance, if you have 20 dB MV on the input, and the MV again is the suffix because we're measuring a change in millivolts, and our output is 40 dB MV, our gain is in dB, right? Because we're talking like for like, and the answer in this instance is obviously 20 dB, right?
Well, I was starting to question myself, but yes, it's 20 it's 20 dB. Yeah.
I promise I'm not trying to trick you again.
I know.
Um,
Well, I went down a I went down a mental rabbit hole because I saw MV and then I looked at the MV abbreviation and then I looked at the nanowatts in 75 ohms and this is the weirdo in me and I'm like, well, what happens when it's not 75 ohms? Anyway, and then you asked me the second time and I answered. Um,
yeah.
yeah.
So we use it all the time, right? Whether we're measuring, optical power in our fiber networks in dBm, the decibel milliwatt, and typically that's how we measure optics. And you can measure the loss in your optical link because you know what your output power of your transmitter is in dBm and your input power in your receiver also in dBm, and the difference is in dB. Same thing with your gain and your losses, and we'll talk more about those. But you can append a suffix onto it for a bunch of different things. DBC is another one that maybe doesn't get used a lot, but it is pretty important. Um, and the use case for me that comes to mind on this one, Scott, is certain leakage um, detection equipment, and you insert a marker or a carrier into your signals, your downstream broadcast signals, to then do leakage detection in the outside plant. And so you put that marker tone in between two carriers and you adjust its amplitude, not necessarily in dBmV because it's relative to the channel that's beside it. So the typical setup would be like 30 dBc or 30 dB below the adjacent carrier as a reference of that relationship between those two carriers. So that's an interesting one that I hadn't really thought about, I guess, before.
Yeah, I think moving into 2026 and beyond, we're really going to be looking at dBmV and dBm. Maybe some of these antenna gains in terms of leakage. I think you mentioned inserting a little CW. I think those days are almost gone, right? With digital leakage and everything else that we're doing in modern HFC systems.
Yeah, they're still out there though. Yeah, and the leakage receivers have gotten much better at reading like pilot tones within or OFDM downstream channels, and also burst energy from OFDMA. So yeah, but going all the way back, we would insert like an analog CW carrier into the broadcast and then look for that. And then they moved into this, really, really small marker. But anyway, not to get too far down a rabbit hole, as we are wont to do.
Yeah, we do that all the time.
So the dB is really important, but it's also important to talk about the suffix when you're talking about absolute measurements, like signal levels. Okay, use cases. Haha. I promised we would come to this. And back to the splitter and combiner examples, because this is actually also really useful. So these are scenarios where you can refer to the dB as just the decibel, provided that we're comparing like for like. So this is one, again, back to my early days in cable 30 years ago, where I didn't understand why the loss of a splitter was 3.5 dB, right? And this sort of makes it make sense, where you have an input signal, and then it is equally divided through some circuitry into two different outputs. So in other words, it's divided approximately in half.
Yeah.
And if we go back to the other chart, it says when we divide a power in half, that's a loss of approximately 3.01 dB. Now, the other half or so of loss is based on the circuitry, or the loss properties of the electronics inside of the splitter. So it's pretty accepted that a two-way splitter is 3.5 dB of loss, depending on frequency and manufacturer, from the input to the output. Now, port-to-port isolation is another thing that can be measured in dB. And I think we alluded to, well, actually, we haven't alluded to it yet, but we're going to. We'll talk about return loss and loss also at the end of the next episode. But carrier to noise ratio, modulation error ratio, signal levels, and the differences between signal levels can all be measured in dB. But talk to us about maybe port-to-port isolation, Scott, and why that's important, and maybe what it means a little more in detail.
Well, I think the biggest reason that I find it to be important is, especially in a tap module, where you really need to isolate drops from each other. And I'm sure everyone here, or if you've not yet and you're in the field, you're going to find a time where your neighboring drop is going to be the ingress problem that's affecting the drop that you came to visit. So you go to trouble call at 123 F Street, and 125 F Street is actually the bigger offender, and the port-to-port isolation on the tap is not high enough. And what we mean by that is, as the circuitry in the splitter or the tap, and by the way, if you're not aware, a tap does contain a splitter or a directional coupler and a series of splitters. And those splitters, again, have inductors, resistors, and capacitors that route signal and also have some small filtering functions. But basically, you want to keep the signals going the directions they were meant to go, and not kind of floating around backwards. And I love the diagram that you've got in terms of the isolation with the input terminated. So this is a fun one. If you've never done this, and I've actually needed to do this before, there was a time when return noise was bad enough we would pad it. I don't think that's a practice in some MSOs now, but back in the day, that's what you did. And I remember a day where I didn't have a 20 dB attenuator, and I called a buddy and I said, "Hey, do you got any attenuators?" And he says, "Yeah." Why you were out? "Yeah, I don't have any." He's like, "Of course you've got one. Take a terminator, put it on the input of a two-way, and run that in line with your drop." And I said, "You want me to do what?" And he said, "Yeah, think about the port-to-port isolation." And I was thinking, oh yeah. So I tried it, and sure enough, in whatever splitter I was using at the time, it was roughly 18 or 20. I'm sure the math here for 25 is probably accurate because the monograph people wrote it, and I'm sure they did the math. But that's my impression of port-to-port isolation. I don't think we need to get too much more technical in the amount of time that we have, but it's definitely useful. we have to keep the signals going the directions they were intended to go, and the port-to-port isolation in splitters and taps are built in just by design, so that we can get that.
And that number, I think, is increasingly meaningful. So I'll pose another example in this particular port-to-port isolation example. Now let's imagine that the input is not terminated and that you had, a drop connected to the splitter. This leg was feeding a cable modem, and this leg was feeding a video set-top box.
Okay.
So there are return signals coming from each of those devices back towards the head end, right? So your video set-top box has typically an out-of-band data carrier that it communicates on the upstream, but your modem also has live energy that it has to transmit back to the CMTS in order to remain connected to the network, right?
Right.
Now think about the disparity between those two levels. Your typical downstream video QAM signals are inside the premise at the input to the set-top box are typically very low, let's say plus 10 dBmV to minus 10 dBmV, right? Okay. Similarly to the cable modem, your downstream input signals, according to DOCSIS specification, should be between plus 15 and minus 15, right?
Okay.
However, your modem also transmits upstream back towards the CMTS at a much higher amplitude, sometimes in the 30, 40, 50 dBmV per channel, up to 64 dBmV of total composite power back towards the CMTS in order to overcome all of the upstream path losses and arrive at the CMTS at 0, or whatever the desired level is.
Yep.
So imagine your modem is transmitting at 45 dBmV per channel on the upstream into this two-way splitter. Now, the desired travel path is through to the input back towards the CMTS into the drop cable. However, some of that energy actually is dependent on the port-to-port isolation of the drop splitter. And so some of the modem's transmitted upstream energy can end up actually being rerouted through the other port of the splitter and onto the front end of the video set-top box. Why is that important? Because we actually have seen in mid-split and higher and high split, some of that energy actually hits the front end of the tuner in the video set-top box because it has a diplex filter, typically that is a sub-split diplex filter. So anything above 55 megahertz would actually be seen by the front end of the set-top box's tuner and could be construed as energy that it's supposed to see and actually cause video tiling problems. And that is primarily dependent on the amount of port-to-port isolation in that two-way splitter. So that's another pretty common scenario. And if you wanted to measure the amount of isolation that your splitters have, whatever splitters you use, you can do that. Inject a signal into one port of the two-way splitter, terminate the input, and measure how much comes out the other side. So that's another reason. Oh, and it will be measured in dB rather than dBmV.
Of course. So total off-the-cuff question. If I wanted to get rid of that, I'll call it extra total power that goes into the set-top box, could I put a 10 dB attenuator pad on the drop cable that goes to the set-top, and would that solve the tiling problem? Or would I still have a tiling problem based on too much power coming back through?
Well, as Ron Rannick likes to say, it depends. If you put the attenuator on the leg going to the set-top box, you would decrease the amount of energy that was transmitted to that port from the adjacent port by the amount of the attenuator value. However, it would also attenuate the input signal or the intended signal.
Yeah. So, okay, so it'd be a wash. It wouldn't.
It could be, yeah, because your input to your receiver would actually get lower, even though the incident signal from the modem would also get lower.
Got it.
So it is a bit of a wash. So that's a use case. Okay, is that the end of our show? I think it is. So that is the end of this particular episode on the decibel. And I think, that was an interesting conversation. So next time we get together, I think we're going to talk about the velocity of propagation and what that one is. Yeah.
I'm interested.
Yeah, me too. All All right. Well, thanks for that conversation, Scott. I think that gave us a better understanding of the decibel itself, what the real world implications and applications are, and how not to misuse it um, with respect to the suffix in absolute measurements. So, okay, everybody, thanks for hanging out with Scott and Mike as we dig into the technical monograph series. And when we come back next time, we're going to talk about velocity of propagation. So come back and see us again.
See ya.